Hello everyone. Once again, welcome to our online physics classroom. Hope all of you are fine and safe at home. Children, in the last session we have gone through magnetic field produced due to a current carrying straight wire or conductor. We have seen that the magnetic field occurs in the form of concentric circles around a straight wire. We also discussed about a rule that can be applied to find out the direction of the magnetic field around a straight conductor. Do you remember that rule? Yes, Maxwell's right-hand thumb rule. Today, we will discuss about a magnetic field produced due to a current carrying circular loop. So children, let's get started with today's session. Magnetic field due to a current carrying circular loop. Children, as you know, whenever current passes through a straight conductor like this, it produces a magnetic field in the form of concentric circles. By applying Maxwell's right-hand thumb rule, we can easily find out the direction of the magnetic field. So here current is flowing upward, so the magnetic field will be acting in the anti-clockwise direction as per right-hand thumb rule. Similarly, if the current is flowing downwards through the straight conductor like this, what will be the direction of the magnetic field? Yes, magnetic field will be acting in the clockwise direction like this. So you must remember this particular direction or concept of the magnetic field. Whenever current flows upward, magnetic field will be anti-clockwise. When the current flows downwards, magnetic field will be acting in the clockwise direction. Now, if we take the same straight wire and if we bend this straight wire in the form of a circle like this, it forms a circular loop. Okay, and if we connect the ends of the circular loop to a battery, what will happen? The current starts to flow through this circular loop. And whenever current passes through this circular loop, it acts like a magnet and it generates a magnetic field around it. So let's try to visualize the magnetic field due to a circular loop through an activity. So just have a look at this activity.
Over here, we find that the conductor has been placed in the shape of a loop and on a plastic board with two holes in it. Now, when there is no current flowing, the iron filings are randomly placed. Now, what happens as soon as current starts flowing? Observe closely. The moment current starts flowing in the current carrying loop, a magnetic field will be generated and the pattern of the magnetic field will be given by the iron filings, as you can see. Over here, the iron filings are no longer randomly generated, but they have arranged themselves in a particular pattern around the current carrying loop.
Children, did you notice the pattern of iron fillings or the alignment of iron fillings in a circular coil? They were arranged themselves in a definite pattern, and this was the pattern, right? So near the coil, the magnetic field lines are crowded like this. As we move away from the coil, the magnetic field lines are farther apart. Here also, near the wire or the coil, the magnetic fields, the circles are crowded, and as we move away from the conductor, the circles are farther apart. The circles represents what? Magnetic field lines. Okay, so here the circular coil is connected to a rheostat, a meter, battery and a key in series. When the circuit is switched on, current flows from positive to negative terminal of the battery. That means the current flow through the circular coil is in which direction? Yes, it will be in the clockwise direction. Or why did we notice such a pattern for a circular coil? So in order to understand that, let's divide the circular loop or coil into finite number of straight current carrying conductors. So here we have considered the circular coil. Ends of the circular coil is connected to a battery. When the circuit is switched on, current flows from positive to negative terminal of the battery. So the current flow through the circular coil is in which direction? Yes, the current is flowing in the clockwise direction. Current through the circular coil is in clockwise direction. Now let's divide the circular coil into finite number of straight current carrying conductors like this. Okay, now each segment in the circular coil or each part of the circular coil can be considered as a straight conductor, right? So this segment can be considered as a straight conductor. This segment can be considered as a straight conductor and so on. Now, consider the current flow through each segment. Depending upon the current flow, we can easily find out the direction of magnetic field of each segment generated around each segment with the help of Maxwell's right hand thumb rule. So here if we consider this segment, here what is the direction of current flow through that? Yes, current is flowing upwards. So if current is flowing upwards, what will be the direction of magnetic field? Yes, in today's session also we have discussed the same thing. When current is flowing upward, magnetic field will be in the anti-clockwise direction. So around the segment a magnetic field is generated, and what is the direction of that magnetic field? It will be in the anti-clockwise direction like this. And if we consider any segment on this side of the circular coil, let this be our left hand side of the circular coil and let this be our right hand side of the circular coil. If we consider any segment on the left side of the circular coil, what will be the direction of current through that segments? Is it upward or downward? Yes, the current will be flowing in the upward direction through all the segments on the left hand side of the circular coil. So what will be the direction of the magnetic field lines around each segment? Yes, it will be anti-clockwise. Through this segment, what will be the direction of current? Yes, it will be anti-clockwise. And if you consider this segment, what will be the direction of current? Yes, it will be anti-clockwise like this. Now, consider the right side of the circular coil. Just consider this particular segment. What is the direction of current flow through that? Through that segment? Yes, current is flowing downwards. Okay, so when we come to the right side of the circular coil, what is the difference? Current is flowing downwards. On the left side, the current flow was in the upward direction, but on the right side, it is in the downward direction. So as per Maxwell's right hand thumb rule, whenever current flows downwards, what will be the direction of magnetic field? Yes, magnetic field will act in the clockwise direction. So through this segment, a magnetic field is generated and the direction of that magnetic field will be, yes, acting in the clockwise direction. So this is the clockwise direction. And if we consider any segment on the right side of the circular coil, what will be the direction of the magnetic field? Yes, direction of the magnetic field will be clockwise itself. So here also the direction of the magnetic field will be clockwise. Okay, so this is about the pattern of magnetic field lines on two diametrically opposite ends of a circular coil. So it's an amazing fact, right? Within the same circular coil, on the opposite ends, we have two different directions for magnetic field. On the left side, through which current is flowing in the upward direction, magnetic field will be in the anti-clockwise direction. And through the right side of the circular coil, where current is flowing downward, magnetic field will be acting in the clockwise direction. Now let's again focus on the left side of the circular coil. On the left side, here in this part, in this area, what is the case of the magnetic field? Is it entering into the screen or is it coming out of the screen? Yes, if we consider the inner side of the coil, that means the face of the coil. See this area, this portion of the coil, the center of the coil can be considered as the face of the coil. We will call it as the face of the coil. So if we consider the face of the coil, what is the direction of the magnetic field lines in the face of the coil on the left side? Yes, if we consider this magnetic field, what is the direction? It is entering into the screen. Here also it is entering into the screen. On this region it is into the screen, on this region it is into the screen. So everywhere on the left side the magnetic field is entering into the screen. So if magnetic field is entering into a point, which pole will be that? Just recall the properties of the magnetic field lines. What is the first property? The magnetic field lines emerges from a north pole and merges or ends in a south pole. So which pole can be considered as a south pole? The pole to which all the field lines are coming or entering. So in this case, on this side, all the field lines are entering into the screen. So this region can be considered as the south pole. Why? Because on this region, all the field lines are entering into the screen. Now let's focus on the right side of the circular coil. When we focus on the right side, here also we can see the same thing. See here the field lines are entering into the screen. On this region field lines are entering into the screen. On this region also field lines are entering into the screen. Right? So here also the magnetic field lines are merging to this point. So this face of the circular loop can be considered as south pole. So the face of the coil will be south pole. The face of the coil acts like a south pole whenever current flows in the clockwise direction through the circular coil.